Hello everyone, this is Karthikeya Lamanchali. On behalf of our group, I would like to welcome you to our presentation on artery-based spatial algorithms covering nearest neighborhood search and skyline search for our course at this Macquarie University. Our group has built all the algorithms from scratch in Python without using any external spatial indexing libraries. Across both tasks, we have implemented 6 algorithms in total, and I will let my teammates walk you through each and everything we did, how we did, and why we have made those choices. I will quickly introduce the team and explain how the assignment was structured. We are 3 members. Priya, she worked with task 1, which is the neighborhood search. I worked with task 2, which is skyline search. And Mr. Sriram Damati, he worked for task 3, which is the report generation or the project report. Our dataset was determined by rule using our student IDs. We took last digits of each ID, 4, 8, 2, and added them together to get 14 and computed it with the 14 mod of 3, which is equals to 2. That assigned as the parking dataset with 150,000 points of task 1 and the city 3 dataset with 300,000 homes for task 2. The central goal across the entire assignment was to implement the spatial algorithms from scratch, compare each one against the sequential baseline, and document the algorithm's evidence very clearly. For task 1, Priya has implemented sequential scan, branch and bound with divide and conquer across 150,000 points and 200 queries. For task 2, I implemented sequential scan, branch and bound skyline with divide and conquer across 300,000 homes. Sriram then consolidated everything into the project report with a full functional documentation, algorithm traces, and performance analysis.
Hi guys, I'm Priya and I worked on task 1 which is the nearest neighbor search. And before I explain my algorithms, I need to explain why I built an artery, because every speed up I achieved after comes from this data structure. And the fundamental problem with the spatial data is that there is no natural ordering in 2 dimensions. So if I sort the 150,000 parking spots by x coordinate, that tells me nothing but which ones are close to the y, and I cannot simply use a binary search. I need a structure that understands proximity in 2 dimensions simultaneously. An artery groups nearby points inside minimum bounding rectangles. A minimum bounding rectangle is the smallest rectangle that encloses all the points in a group. On the slide, you can see that there are two rectangle covers the entire space. Inside it, node 1 in blue contains parking lots P1, P3, and P5. And in node 2, green contains P2, P4, and P6. This structure enables pruning. If I already found a parking lot at 2.2365 units away and a user and entire rectangle nearest edge is 3 points, so I can skip everything inside that rectangle without checking any point. As per the construction, when a node overflows, I choose to split the data that minimizes the total parameter. And you can see that in the slide as well at the bottom, where it shows inserting P4 causes to overflow, and X split gives the parameter of 11 while Y split gives the parameter of 13. So I choose X. I always minimize the parameter because the tighter the rectangle means the more aggressive pruning later, and a looser rectangle means forcing unnecessary exploration. A tight rectangle gets eliminated faster. The problem is very simple. 150,000 parking locations, 200 users, return to the closest parking spot for each user. The spatial query example on the right shows that user Q at coordinates is 8,6. The nearest parking lot is P4 at coordinates 9,4. Within the minimum distance is 2.23. All the three of my algorithms find the exact correct answer, but with the different amounts of work. I implemented everything in Python as required with no external spatial libraries. And the sequential scan took 7.82 seconds as the baseline, and branch and bound took 0.092 seconds, which is 85 times faster, and branch and bound with divide and conquer took 0.030 seconds, which is 258 times faster. And let me explain exactly how and why. Sequential scan checks all the 150,000 parking points every single query. 200 queries multiplied by 150,000 points equals to 30 million distance calculations. It took 7.82 seconds. The reason it's so wasteful. It has no spatial awareness. It computes distance from every parking lot to another side of the city. Even though those lots clearly cannot be closest, every point is checked regardless. So when it comes to branch and bound, fixes this issue using a value called minimum distance. A minimum distance is the minimum possible distance from a user to any point that could exist inside a bounding rectangle. It is a distance to the closest edge of a rectangle, not to any actual parking lot inside it. The pruning rules follows directly. If the minimum distance of a rectangle is already greater than the best distance I have found so far, then every point inside that rectangle is also guaranteed to be further away. The region cannot be possibly improve my answer, so I skip it entirely with one comparison. I use a priority queue ordered from the smallest minimum distance to the largest. This is a deliberate choice. By always exploring the most promising region first, then I find a good answer quickly. That good answer always tightens my pruning threshold early, which eliminates even more regions rest of the search. So this algorithm becomes the self-reinforcing. On the right hand side, you can see that node 1 has the minimum distance of 3.0 and gets pruned. Node N2 has minimum distance of 2.0 and gets processed first. Inside N2, we find the P4 at the distance of 2.236. When we check N1, its minimum distance is 3.0, already exceeds the 2.236. So the entire node is eliminated. Result is 0.092 seconds, 80 times faster than the sequential scan. This slide traces the exact execution on a query queue at a position 8, 6. I want to go to each step because it shows the pruning is not a heuristic or an approximation, it's a mathematically guaranteed step. So in step 1 we can see which is initialization, and it's an initial search as we can see in the slides. Best distance is to set infinity. Best point is none. A queue starts with the root because every parking lot is somewhere inside it. And step 2 is calculating the minimum distance from both the children nodes. Node N1 has a dx equals to 3 and dy equals to 0, giving minimum distance is 3.2. And node N2 has dx equals to 0 and dy equals to 2, giving minimum distance 2.2. Q becomes N2 first, then N1. And step 3 is visiting N2. It is a leaf, so we check its actual parking lot directly. P2 coordinates 8 comma and gives a distance of 5.0, which is P4 at coordinates 9 comma 4 gives the distance of 2.236, which is better. Best updates to P4 at 2.236. And step 4 is the critical moment for us. We pop N1. It's the minimum distance is 3.0. Our current best is 2.236, which is 3.0 greater than 2.236? That's the main question. And the answer is yes. As for this slide states, no point inside N1 can improve the current best answer. We prove N1 entirely. P1, P3, and P5 are never checked. Sequential scan checks all 10 sample points. Branch and bound checked only 2 points and proved N1 was useless with a single comparison. 50% of the tree was skipped, and on 150,000 real parking spots, this effect is what produces 85 times better speed up. Here, my third algorithm adds the divide and conquer on top of branch and bound. The key insight on this slide is that the shallow tree reduces search the depth while the final comparison preserves the exact correctness. And on the artery bill, 150,000 points, one is the deep, while branch and bound has to traverse many levels before reaching the actual data. I asked myself whether I could make this tree shallower without losing the correct answer. What would it be? And the solution I came up with is to split the 150,000 data parking points by the median of x coordinate into two balanced partitions, which means each of the two parts gets the 75,000 each, and each partition gets its own R tree. While both trees are built once and reused across 200 queries. For each query, I ran the branch and bound on both trees to get the nearest neighbor from the each half and return whichever is closure. The correctness is guaranteed because the true nearest parking lot must exist in one of the two halls, and I never miss it. Two trees of 75,000 points are shallower than the one tree of 150,000 points. Shallower tree means branch and bound reaches the data faster, bounding the rectangles tighter, making the pruning more aggressive. And the result table clearly confirms it, as you can see in the slides. Sequential scan of 7.82 seconds, branch and bound is 0.092 seconds, which is 85 times faster. And divide and conquer, which is our ultimate winner, has 0.03630 seconds, which is 258 times faster. While the required target was to get at least 5 times faster than the previous method, but both algorithms far exceed that. This is the result for my task, and now I'll hand over it to Sriram for the report and task 3 explanation. Thank you.
Hello, this is Kartikeya Yalamanchali. I worked on task 2, which is skyline search on 300,000 homes for the city 3 dataset. The problem is different from the nearest neighborhood search. Here, we are not looking only for one closest point. We are looking for a whole set of homes that represent the best possible trade-offs across the two attributes. Each home has an X value, which is the total purchase cost, and a Y value, which is the price per square meter. The concept at the center of this problem is dominance. Home A dominates home B if A's cost is less than or equal to B's cost, and A's price per square meter is less than or equal to B's price per square meter, which is at least one times being those strictly less. In plain English, A is at least as good as B in every way, strictly better in at least one way. If that is true, no rational buyer would ever choose B when A is available. The skyline is complete set of homes that are dominated by any other home. These are called the Pareto optimal choices. They represent every meaningful trade-off available. If you want the cheapest home possible, the skyline shows the best price per square meter you can get at that cost. If you want the best price per square meter, the skyline shows the cheapest cost you can get for the quality. On the scatter plot on the right, you can see the skyline homes in green sitting towards the bottom left corner and the dominated homes in gray scattered further up towards the right. The bottom left is always better because it means cheaper costs and also the better value at the same time. The arrow on the plot shows P4 at the coordinates 8, 3 dominating P2 at the coordinates 11, 5 because 8 is less than 11 and 3 is less than 5. The native approach is comparing of every pair of homes. With 300k homes, that is roughly 45 billion comparison, and sequential scan took 2.02 seconds. I need to eliminate most of these comparisons intelligently. My second algorithm is branch and bound skyline. The name corners from the same branch and bound strategy Priya has used before, but adapted from the skyline problem instead of the nearest neighbor. For nearest neighbor, we prune the regions that were too far away from the user. For skyline search, we prune the regions that are completely dominated by the homes already in our skyline. The pruning rule is different, but the core idea is same. Eliminate the entire regions within a single check. The key insight that makes this work is lower left corner of a minimum bounding rectangle. Think about what lower left corner represents in our coordinate system. It has the smallest x value and the smallest y value of any point that could exist in the rectangle. It means the cheapest possible cost and the best possible price per square meter is simultaneous. It is the best home possible that could exist anywhere in that region. Now, here is the pruning rule. If a home already is in my skyline, dominates the lower left corner of a rectangle, then the skyline home is cheaper or equal and has a better or equal price per square meter compared to the best possible in that rectangle. This means every single home inside the rectangle is also dominated by my skyline. I can prune the entire rectangle without checking any of the homes inside that. The algorithm process nodes in a priority queue ordered by the sum of x plus y from smallest to the largest. This ensures we discover the strongest skyline homes early, which makes our pruning more aggressive for the rest of the search. We can reach a leaf node to check and update the skyline, like actual homes, and update the skyline. When we prune a node, we skip all its children automatically. You can see the lower left minimum bounding rectangle example on the right side of the slide. The orange rectangle has its lower left corner at the coordinates of 11, 2. A skyline home already found dominates that corner. Therefore, all 5 homes inside that rectangle are pruned with just one comparison. The result is 0.0010 seconds, which is 2022 times faster than the sequential scan. This slide explains my third algorithm, which combines branch and bound skyline with divide and conquer, introduces one-dimensional dominance screening during the merge. Stage 1 is dividing by cost. I split all 300k homes by their median x value. The left side contains the cheapest homes where x is less than or equal to the median, and the right side contains the pricier homes where x is greater than the median. The split is the foundation of everything that follows because it creates the guaranteed ordering between two halves. Stage 2 is running the branch and bound skyline independently on each half. The left half produces its own local skyline, which is P7, P3, P4, and P9. These are the best homes among the cheapest options. The right half produces own local skyline, which is P14 and P8. These are the best homes among the pricier options. I now have to separate two local skylines that need to be merged into one final correct skyline. Stage 3 is where one-dimensional dominance screening comes in. The slide stages the key point directly because the left x is less than the right x. The merged only needs to check y dominance. Here is why. Normally, to check if one home dominates another, I need to compare both x and y. But because of how I divided both the data of every home in the left half has a smaller x value than every home in the right half. This is not a coincidence. It is a direct sequence of splitting by median x. So when I'm merging, And checking whether the right side home should be removed, I ask, does any left side home dominate it? For that to be true, the left home must have smaller or equal x value and smaller or equal y value. The x condition is already guaranteed by the split. So one thing I actually need to check is y. That is what the merge simplification box in the middle diagram says. Left side x values are already no worse than right side x values. So the merge reduces to comparing only y values, which is one dimensional dominant screen. Stage 4 shows the result from the right half skyline of P14 and P8. I check both against the left skyline using only y values. P8 gets removed because left home has a smaller or equal y value. It means that P8 is dominated. P14 survives because no left home has a y value smaller than or equal to P14's y value of 1. The final skyline is P7, P3, P9, P4, and P14, which are 5 homes. Looking at the performance results on the right, the zoom box confirms that the branch and bound skyline took 0.0010 seconds and the divide and conquer took 0.0009 seconds. The difference is 0.0001. The note the bottom of this slide puts this clearly. Divide and conquer gives a most modest sequential scan took 2.02 seconds. The branch and bound skyline took 0.0010 seconds, which is 2022 times faster. The branch and bound skyline with divide and conquer took 0.0009 seconds, which is 2244 times faster. Both far exceeds the required target of at least 5 times. I will now hand over this task to Sriram.
Hi everyone, I am Sriram Dumati. I worked on Task 3, the project report. The project, the report demonstrates understanding by explaining the reasoning behind our complication decisions, not just code itself. The report contains three sections. First, function documentation. We documented all 23 functions, including inputs, outputs, time complexities, and relevant lecture topics. We also included 8 additional functions such as node.parameter, node.is overflow, and node.is because they are essential to how the algorithm operate. Second, algorithm traces. We traced four important processes. They were R tree construction, showing node overflows and split selection, branch and bound nearest neighbor search, showing minimum distance calculations, and pruning. Branch and bound skyline, showing lower left corner dominance pruning, and divide and conquer skyline, showing how one-dimensional dominance screening reduce merge complexity. These traces justify pruning decisions and make the results reproducible. Third one, updated specifications and corrections. The final result shows nearest neighbor search running in 0.030 seconds, achieving a 258x speedup, while Skyline search runs in 0.0009 seconds, achieving a 2244x speedup. During testing, we discovered that the divide and conquer Skyline timing incorrect included artery construction time. Since branch and bound skyline excludes construction time, this created an unfair comparison. After separating construction from search time, the corrected runtime became 0.0009 seconds. We documented this corrected transparency in report. So this slide summarizes our achievements. We built a custom artery form stretched without external libraries. Im- Implementing every insertion, split, overflow, and MBR update ourselves. Branch and bound achieved an 85x speedup by pruning regions using minimum distance. Divide and conquer increased this to 258x speedup through two shallower trees. For Skyline search, branch and bound Skyline achieved a 2022x speedup using lower left corner dominance pruning. Divide and conquer improved this to 2244x through one-dimensional dominance screening. All algorithms exceeded the required 5x performance target. Our lowest speedup was 85x and our highest was 2244x. The key idea across all tasks is the same. Use mathematical properties and spatial indexing to eliminate large part of the search space early instead of performing excessive comparison. Thank you. Thank you for watching.